All right. Now, all of you found out why students have so much difficulty with this sometime yesterday, didn't you? We kind of got real thick yesterday, and it got very interesting. So I'm trying to make some generalizations, and this is in the 44 notes, but I just wanted to talk through this a little bit, okay? If you've got one function, and generalizing doesn't mean it's true always, but most of the time, if you've got one function, that's going to mean there's only one wall of it that you're making. That should mean there is no void. Okay? Do you know what I mean by a void? There's no hole in it. It's going to be a solid figure. If you've got something like that, it ought to look like this. Pi r of x squared. Now that r might be the function. It might be the function minus something else, but that's what it should be. And I think I told you wrong on D part now that I think about it, okay? We need to look at that in a second. Anytime you've got two functions, that should mean two walls there, okay? If you've got two walls, then you should have something that looks like this. An inner wall and an outer wall, okay? And still, obviously, the pi in there. That's the hard part for students, is seeing the difference between those two there, okay? Remember that your r right here is always the radius. It's the distance from the function to what you're rotating it around. Sometimes it's the function itself. If the function is something different than the x or y axis, it's probably something different though. So you just have to be careful with that. Always know those are the two pieces that students have a hard time with. Rotating left and right, this way, this is left and right, okay? That's with respect to y. Rotating up and down means that we're integrating with respect to x. Those two are easy for students to get at. So as you looked at your assignment last night, what did you find? This is the one you were, 12D is what you were asking about, right? Let's look at 12D right quick, okay? We can look at other pieces if we need to there. Yes, sir. Yes, you may. If you were to graph this thing out right quick, we get something that looks like this. That's y equals 2x squared. Y equals 0. X equals 2. So this is the region that we're rotating around something with, okay? Now in D part, press the little triangles up or down. It's locked. Hit mode. Hit mode until it says air or cool or something like that. Does it say anything? Yes, you can program it to come on and come off. And oh my goodness, it's not going to be immediate. Okay, we want to. Oh my goodness, you're into programming this thing. Jeez, I didn't do that. It was like that. Oh, there we go. Program, fan on, cool, 72. Boom. There we go. All right, now back to this. We're taking this region. D part, we're rotating it around the line x equals 2. That's this line right here. So we're rotating it that way. We've got that region that we're rotating. So now, let's first of all, when we rotate this around, are we going to have a void in the middle of it? No, because we've only got the one function. You look at the colored in area, and it's right up next to the axis. So we're going to just have one thing that we're rotating around. So we know we've got an integral, something in here, squared. Are we dx or dy? Dy, because we're going this way, okay? So we know that much. Our limits of integration, we're going from here up to here. I believe you'll find that that's 0 to 8. Yes, 0 to 8 is what you'll find that to be. Because when x is 2, when I put 2 in there, I get 8 out of it. So I'm going from 0 to 8. The question is what's in there. Okay? How do we figure out what's in there? What's the radius? The radius is from the axis to the curve, that piece right there. How long is that piece right there is the question. Now, it's not the function. The function, if we solve this out, we get the square root of y over 2, I think, for x. Where is that distance on this picture at? That distance is the square root of y over 2. Okay? What distance is this here? How can we find that out? Well, it's going to be this whole distance here minus this up here, the black line that I've drawn here, minus that y over 2. The black line is 2, so we should write in 2 minus the square root of y over 2. That whole thing squared, and we're integrating from 0 to 8. Were you, hallelujah, you got it right. That's what I want to hear. Okay, yes, ma'am. Okay, you wrote down this. Okay, now, this would be, think about physically making. This says I'm going to cut out a swath too wide. I'm going to make this thing, and then I'm going to cut this out right next to the axis. I'm going to cut out this piece here. That's not what you're doing there, okay? This inside piece is right around the axis always. So that I see how you could get to that point there, but that's cutting the inside of it out. What you were thinking, you mean, is I'm going to take this and then I'm going to cut out this piece over here. You were thinking about cutting out the outside piece there. Why wouldn't that work? That's 2 squared. That distance, yeah, I think that would cut out the reverse of what you need there. But the biggest thing, the easiest way in my mind to think of this is think about physically making this. There's not a void in there. This region is swept all the way to the axis, so there's only one thing to square in there. All right? Was there another one of those ABCs that we needed to look at for number 12? C part. So let's look at C part. We know we've still got the same picture. Y equals 2x squared. Y equals 0. X equals 2 for this region. Now, the line y equals 8, we know is right here where they intersect at. How do we know it's right there? Because we know this point here is 2, 8, remember, from putting it in there. So that's a big piece of it, knowing that right there. Now we're going to rotate it around this line. So that tells us dx or dy? Dx, all right. Pi. Limits of integration, Joan. 2 to 0, 0 to 2. Now, do we have a void when we sweep this thing around? Jonah, can you see the void here? Because we're going to rotate it around this line here, this little triangle. So if we rotate that around, we're going to have an inside bowl there. You see that? So since we got a void in there, since we're going to have an inside bowl to it, we know we've got something squared minus something squared. Okay? Now, the first something is the furthest thing away. That's this distance right here. 8, or 8 minus, actually, 8, yeah, 8 minus 0 squared, or 0 minus 8 squared, okay? I'm going to write it like that. What is that distance right there? All right. Now, do you see that this distance here that I'm drawing in red, that distance is going to be 2x squared every time, because that's the y value. So then this distance up here is not 2x squared, it's the whole distance, the blue distance that we had, 8, minus that red distance, 2x squared, and then that whole quantity squared. Does that make a little more sense there? Okay, good, good. Any others from that assignment last night that you needed to look at? I don't know. 13, part B, said the line y equals 6. All right? So I gave you a picture on this. Where's the line y equals 6 at? Up above my head, up here. Boom. So now, we're rotating this figure around. Kelsey, dx or dy? Dx, okay. Pi. What are my limits of integration going to be? 0 to 2. All right, Kelsey, do I have a void when I sweep this thing around? Okay, so that means I've got something squared minus something squared. All right. Now, Claire Daniel, what's the first something for this one, you think? 6. 6 would be the distance from here all the way down to here, right? Is that what we're sweeping around to begin with? I thought aren't we just sweeping this region here around? We just need to sweep that region right there around. So what's going to be our first, what do y'all think? X squared? Okay. This red curve is x squared. This blue curve is 4x minus x squared. So Jerry says x squared. Y'all think so? Yiming says 6 minus x squared. All right. You have to do the minus because we know there's going to be a void in the middle here, okay? Think about making this figure. I'm going to take this red curve here and sweep it around the line. So that's the first thing. So it's got to go in here. So how far is it from the axis to the red curve? Okay? 6 is the total distance all the way down here. X squared is the distance up to the red curve. So we're looking for 6 minus x squared and the whole quantity squared. Y'all see that? Okay. What about for the next one? For this blue curve, we're looking for that distance from the blue curve up. 6 minus the other one, 4x minus x squared. 6, I wrote that wrong. 6 minus 4x minus x squared, the whole quantity squared, dx. And you don't want to work these out without a calculating device. Okay? That's hard to see. Very, very, very hard to see. It gets better with time. By May, you'll be okay with it. Hey!
What if you were going to, rotate that thing around, x equals 1, where the line, through it? Can that happen?
Terry asked that a while ago. What if we were going to rotate it around a line right slap dab through the center of it? Cry. Okay? Because I don't know how to do that.
Okay.
I won't give you one like that, all right?
They give us one. Is that possible?
Is it possible? Well, yes and no. I mean, if you split them up, part of this one that you're rotating around is going to be over this one down here. So if you think of it as physically making two shapes, you are...
Then you could split it up, mirror the function, find out what's going to overlap and subtract.
That's what you'd have to do. You'd have to split it up, then mirror the function over, then take out the subtraction, and then rotate the mirrored part, and that would just be terrible to do.
Would they give us that on the exam?
No. I've never seen anything like it. I don't believe it. I don't believe it. I mean, Maybe you can prove me wrong, but I don't believe I did that. If I did, let's put it this way: you're the first student in 5 years to have recognized that I did that. Okay. Well, maybe I'm wrong. Maybe I'm wrong. Let's look at this. WebAssign on volumes. Which one do we think it is? But we'll know it when we see it. That's not what I wanted to do. We're not going to add anything to this. Jonah, do you remember which one this might be? The one that says there's a line down the middle of it to sweep around. Number 5. The volumes of the solids generated by revolving the regions bounded by the graphs of the equations about the given line. That's the same problem we just worked there. Let me look at Jonah's. Jonah, do you mind if I pull yours up specifically up here on the board? Okay. All right, so we're looking for scores. We get to see who has started and who has not started. Let me guess, Jonah has started and no one else has. Jonah has started. And let's see. 1. He's done 4. 5. My guess is that, since that's where you stopped, do you think that's the one y'all asking about? Okay. About the x squared is going to be up here. 6x minus x squared is going to be something, what's it going to be, like this? Yeah, it's going to look something like that. So you're going to have this, rotating it around the x-axis, that region is not going to be. The line y equals 10, hopefully that's where these are, is going to be up here somewhere. So I don't think that splits it down the middle. If you find one that it splits down the middle, I really would like to see it, but I don't think you're going to find that. That would be even more cruel and more unusual. Okay. Well, let's talk about the final piece of the puzzle today. Yes, I didn't bring any for you to eat, okay? But what about finding the volumes of things that you can't make by rotating it around?
Well, for the bread, couldn't you find like a surface area of the very
Okay.
and then just multiply by volume?
Well, that's kind of the question that I want to ask here, okay? And these shapes that you're looking at are very simple shapes that I'm thinking about here, really. But think about this shape here and trying to find the volume of that, okay? If you're trying to find the volume of it, do you see that all of the shapes are the same if I were to cut cross sections through here? If I take a knife and cut through the bread, and I'm not a very good artiste, so you're going to have a hard time visualizing, but pretend a loaf of bread you've got sitting on your counter at home that's moldy. All of the pieces are basically the same shape. Agreed? Yeah. Now, what's different about the front one and the next one? And at the front, it's a little bit, normally they're a little bit smaller, aren't they? And then they get a little bit bigger. And have you ever done, y'all may not be this paranoid, but if you ever take out, well, y'all don't make sandwiches for 4 or 5 people at a time. I make sandwiches for my whole family at home. I get out 8 pieces of bread. If you take the first piece and the last piece and try to match them together, they don't match exactly. Have you ever noticed that? Try it sometime. Because if you want them to match perfectly, it's got to be 2 pieces side to side. And sometimes if you turn the piece of bread over, they don't match up exactly. And that's just a fraction of an inch. Yes, that's a paranoid problem. I'll agree with you there. But if you get 7 or 8 pieces separated, it's a big difference between them. So how can we find the area of something like that? Well, let's stretch it out even more than that. What about the area of some really funny shaped house that looks like this? That's a messed up house where you don't have any corners in the whole house. There's not a single corner anywhere in the house. Yeah. But see, you've got this odd roof line there. I mean, how do you find the volume of something like that? Or what if you really want to get way out as an engineer and you're going to design a house that is triangular in shape, but it goes back to a single point back there. So in the furthest regions of the house, it's just a corner. But as you come out, each piece gets progressively bigger and bigger and bigger, and it's a triangle.
That's not awful. Take a pyramid and cut it in half and flip it over.
But if you take the pyramid and cut it in half, but I'm talking. But no. But I'm talking about the point is at the back of the house. Flip it on its side. But now all these are squares. I don't want squares. I want triangles for the sides.
Oh, so you want to use
Yes, there's going to be an A-frame house. It's going to be an A-frame house, but the A-frame is going to get smaller the further back you go. So when you get real funky shapes like that, how do we find those volumes? And the answer is we can't find the volume of everything you can imagine with calculus. But anything that can be rotated, like we've just done, we can find. And anything where the cross sections are of the same shape, we can find. Okay? And what do we mean by cross sections? When we cut it up, just like the loaf of bread, when we cut through the loaf of bread, all of those are the same shape. Yes?
Wait a minute, we can't do that with a loaf of bread because on the ends they're rounded a little bit, and they'd be perfectly flat on the other pieces.
Okay, but we can. But I see what you're saying with that. But we're going to use calculus, and we're going to take into account that rounding there at the end. Okay, because even though all of these pieces of bread we just said they aren't the same exact size, if we cut them thin enough, they're all going to, each one we can find the volume of, right? Do y'all follow what I'm trying to say there? If I take a piece of bread, if I can tell you what the area of this front of the bread is, multiply it by how wide the slit is, right? Okay. Now, here comes into play what Rhett said. All right, let's go back and say that again. If I take a piece of bread and I tell you the front of this bread is 8 inches, 8 square inches. If you know that it's 1/4 inch thick, then you can do 8 times 1/4 and say, then the volume of this piece of bread is whatever 8 times 1/4 is, 2 cubic inches. Okay? The problem with that is, as Rhett said, but the one side of the bread may be a little bit different size than the other side. So let's, instead of cutting it a 1/4 inch thick, let's cut it a 1/16 of an inch thick, or even thinner. If we can get it down to enough thin slices, we can find the volume of each one of those slices, and we can add up all the slices. Does that make sense? Now is that practically? No, we can't practically because there's not a knife sharp enough to slice it that thin. We don't want to sit there counting all day, okay? But we can use calculus. And adding up stuff in calculus is called integrating. Okay? So we're going to integrate from A to B the area okay? Now I just wrote that as a large capital A because it's not going to be a specific formula. If the shape is a square, what's the area going to be? Side times side. What if the area is a right triangle? This, and this are the same length, so it's S times S divided by 2. If it's a semicircle, it'll be a different. If it's a equilateral triangle, it'll be different. But as long as we can get some sort of formula here, that's what we're going to do. Yes, sir?
If it's like a cone or something and we don't remember how to do stuff for random shapes, are they going to give us that on the exam?
Some things they would give you, yes. Yes, ma'am.
Like, I thought we were doing like weird shapes. They're not
We
gonna
are.
have, like,
We are going to do weird shapes. We're going to do weird shapes like this. Okay?
a graph.
All right, there's nothing wrong with that. You're right, okay? Let's just stop here for a second and listen now. This is the bottom of it. We're not rotating this around anything. This is the bottom of the figure. Let's see if I can do it. Let me do this. Okay? This is the bottom of the figure right here. What we're going to do is we're going to build our house right here, okay? We're going to make our house a bunch of little rectangles. Each wall is going to be, let's make it a square to begin with. We're going to start here. We're going to go up and we're going to go across. And we're going to go back down. So that each one of these shapes is a square. They're all going to be connected because remember, we've got a blue million of these squares we're going to be making. Every one. So the further back down we go, the taller the house gets. Down here, the house just floats to nothing. But everywhere we go back further, this one's going to be 3 feet across or 3 yards, whatever we want to call it, and it'll be 3 yards up in the air. Whoops, I can't do that. Maybe I need to do it this way. Somebody that's good at drawing 3 dimensions needs to be up here probably. It's going to look something like this picture here. Do you see all of these little clay squares here? We've got all of these squares that we're going to have here. Okay? So our question is, how do we find the area of that there? Can y'all picture that yet? We just need to add up all of the volumes of each one of these individually. Well, I've got 3 million of them maybe. So I can't add. I'm going to have to integrate on it. And what's going to be our formula in here? What? We're going to side times side. We'll get to the specifics in a minute. It would be side times side. However long the side is here times however long the side is here. Is the side going to be a number? Is this side here the same as this side? The same as this side? So the side's not going to be a set number for every one of them. The side's going to be a function. Okay?
But if it's a square, not a rectangle, it's the same.
That's right. It's the same for both of these. So I'm trying to give you a big picture. Now let's go back and work in some specifics here with it, okay? What is this base here? Let's see if I can figure out. Yeah. This is y equals the square root of x. Okay? So here's our question. And here's how the question would be worded for you. Let's go back and just give you the whole worded question here. Okay. The solid has it's going to say solid is perpendicular to the x-axis, and its cross sections are squares. Okay? Perpendicular to the x-axis, and the cross sections are squares. So that's the bottom of my building. So I'm going to come up here at 1, and I'm going to build a wall 1 tall, 1 across, 1 down, and there's my wall. I'm going to come here, and when x is 4, there's the floor. I'm going to go up 2, over 2, down 2. And out here I'm going to go, this is over 9, this is up. I've gone 3 this way, so I'm going to come up in the air 3, come back over, come back down. The graph tells me what shape my floor plan is. That's the bottom of the building down there. So this is where I get to put all my furniture in the yellow down here. This is how high the ceilings are up here. Yes, it does, and I can't draw in 3 dimensions. Yeah, the yellow is an aerial view. The yellow is me looking down at this floor down here, okay? Yes, this is the X and Y axis. Yes, ma'am. Because, good question, how did I know this one was up 3? Because the distance from here to here is 3. See, this distance is 3, so when I come back here, that distance is going to be a little bit less than 3. It's whatever the distance is here, whatever the distance is from here to here. Because see, X is 9, Y is 3. This is my function here. Still hadn't found y'all. Okay. Okay.
I kind of know what you're saying, but
it's very hard to see. All right, let me write down what the integral is, and let's see if that helps any. You're going to be 0 to 9 dx, since we're perpendicular to the x. Our formula was the square root of x squared. Okay. This function here is y equals the square root of x. I would have to tell you that, okay? I did not write it down. I did not prepare well for class today.
So can you just pick any graph, like line your shape up with?
No, whatever graph I give you, okay? So,
They could pick whatever graph they wanted to give.
yes, I could give you the sine of x, for example. Or I could give you some kind of wavy thing and said, okay, this is what it's going to look like. I mean, yeah, for example, if you look at it, it might be easier if you think about this. I don't know. Picture this as being your floor plan for your house, okay? This wall over here, you've got unlimited amounts of money. So you said, don't make it a straight wall. Make it a nice wavy wall, okay? I don't know why you're doing this. You've got too much money on your hands, okay? Now, I want my house overall to get wider in the wide spots and taller in the wide spots and more narrow down here. So I'm going to have a wall, let's say that if that distance there is, 6, then I want it to be 6 feet tall. But when I get back over here, if this is only 5.5, I want it to only be 5.5 tall. So I want my house to have the feeling of when I go into big areas, it's growing up and out. If it's getting wider, it's getting taller. If it's getting narrow, it's getting shorter. Yes, it'd be a stupid thing to do. I don't doubt you at all. Yes. You get paid massive amounts of money if you could do stuff like this. So that's kind of a picture. Let's go one better. Let's go to something you've seen before. How many of you have seen the building in Sydney, Australia, where they sing? The Opera House. Okay. What's it look like?
it's like a shell.
It's a shell. But what's special about the shell? It's curved. It's a curve. Well, maybe we're talking about two different buildings here. Have y'all seen the shells where it's a big semicircle, and then the further back into the stage you go, the shells get smaller and smaller and smaller? Oh, y'all know what I'm talking about there? Why do they do that? Y'all haven't seen the Bugs Bunny cartoon where he's singing, where the opera, where the opera's playing and it's a big shell of a house. Why do they do that? Acoustically, that's not what I was talking about. But yes, that's the Sydney, that's the Opera House in Sydney. I'm talking about a building. I'm talking about a. Yes, 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 yes. We've tried. These are the tops that I'm drawing in now, okay? And as you get out further and further, it's just wider and wider, and it gets taller and taller, okay? So we've got very high up at the top, right at the edge, but as you go back deeper and deeper into the stage, it gets shorter and shorter and shorter. So how are we going to find the volume of something like that? We're going to do what we just talked about. That's the type of shape that we're talking about with something like this, okay? Yes, ma'am.
Okay, so like, is it all like one big, like, is the top like all like one like rounded edge, or is it just like boom shape?
No, the top would be a rounded edge with what we're figuring here.
How is that any different from?
Because everything is going back to one point.
Okay. Does that make it like half of a dome thing or whatever?
No, because we don't know that we're coming out to a half here. We don't have the bottom of it.
So like, is it the same like shape looking thing?
This one would kind of be like a quarter of a dome is what it would be. Because see, to be the whole dome, see, there's a floor to this, so there'd have to be another piece on the bottom and two over here to make it a full sphere. So yes, this is like half of a dome, a quarter of a sphere, a half of a dome, yes, that type thing. Except that the dome is going back to a point of zero in this back here. It's when y'all do in art that y'all fade back to a point. You know what I'm talking about? Perspective point. We're fading back to a perspective point here. Okay. Whew, that was hard. I don't think I did a good job of it. Okay. Well, let's take this again. Let's see if we can do it with just a piece of it here. Okay. We know this is y equals the square root of x. This must be the next line. Volumes of known cross-section with the cross-section in the shape of a semicircle.
Oh, wait, we're on the next one now?
Uh-huh. The shape of a semicircle. Now, what does that mean? That means that we've got a big semicircle right there. And then right back behind it, we've got another semicircle that's a little bit shorter because this distance is getting smaller every time. So if I'm looking at it from down here, I see a real wide, real tall place, okay? But the further I go in here, it's leading me back to this corner, and it's getting shorter, it's getting less wide, and it's getting less tall every single time, okay? Horn of cornucopia. Y'all know what I'm talking about? The horn of cornucopia, that's something to do with, this is kind of like a half of it, okay? Just the top half of it. How are we going to find this area, okay? For right now, let's look for clues, okay? Cross sections, they're perpendicular to x. I didn't write it, but that's how I drew it. Perpendicular to x says dx. All right? Dx says our limits of integration are with x, 0 to 9. Okay? Cross section says I don't have a pi out here by default, okay? I can have one, but I don't have to have a pi out there. Pi is something rotating, okay? In this case, yes, we're going to have a pi in here. But by default, I don't have to have one. I only have to put a pi out. I only put a pi out here if I've taken something and rotating it around the x or rotating it around the y. Now, the shape is a semicircle. How do I find the area of a semicircle? Pi r squared h. That's the area of a semicircle. Well, what is our radius? Our radius, this line that I just drew is our diameter, isn't it? And the diameter is the square root of x. The radius is half of that, isn't it? So what is our formula then? We've got pi over 2 times the square root of x over 2 quantity squared.
I don't get how you draw the shape.
Yes. Yes, ma'am. Completely lost. Can you visualize the picture? No, can't visualize the picture. That's bad when I've got my art students that can't visualize my picture. It means I'm a bad artist. Do I have one of those? I have something like that? No, no. Ah! Do you see that? Yes, I just showed you different little cuts through it. Do you see that that's what I'm talking about? We're looking at this from this perspective back here. See, every one of these is going to be a semicircle, just the width of from here to here. So the further out I go, see, notice these back here on this end, note these here are really big. And the further back we go, they're just getting smaller and smaller and smaller. Now, we could find the volume of these 1, 2, 3, 4, 5, 6, 7 pieces here, couldn't we? But if we want to find the volume of this thing continuously, we've got to integrate that. Okay? Does that help you to picture what we're looking at here? So how would you find the volume of just this one piece right here? It would be the area of this that I'm shading in blue. Well, that's a half of a circle, so it would be pi r squared over 2 times how wide it is there, times the height of it, okay? So how do we translate that into calculus? That translates into calculus as the h is dx because we're perpendicular to the x-axis. Pi and 2 are just numbers. R would be the distance from there to there or from here to here. It's the radius. It's half the diameter. Well, we know that the diameter changes on this every single time. The diameter is the square root of x because we come over 4 up 2. It's the square root of x. So if the diameter is the square root of x, the radius is the square root of x over 2. So that's what I can put there, the square root of x over 2. And it's squared because I was squaring the radius. And then I would integrate that. dx, I'm going from here to here, 0 to 9. Yes, ma'am? dx says that we're cut. Think of it this way. I don't have a great explanation, mathematical explanation, but dx is saying we're cutting these pieces into razor-thin slices that are dx of a amount wide. So that's a very bad explanation. I know that. I'm sorry. That's the best I can give you because it's very hard. I'm not sure I can explain it any better than that. Let's look at a couple more because I really don't think you start understanding these until we work through a few of them. Isosceles right triangle. So we still got the same base here. We still got y equals the square root of x. That's our bottom. Triangles perpendicular to the x-axis with one leg in the xy plane. They're isosceles right triangles. Now, before you start writing down any math, let's get a picture of what this looks like. One of them is 3 feet long that way, 3 meters, 3 yards, 3 miles, whatever you want to think of. It's 3 yards out this way, okay? I can't draw that. Sutton, you're having a hard time seeing this, but I'm holding my finger out 3 feet away from the board, okay? And then I'm going back down from the end to here, okay? So that's what it's going to look like. If I'm standing out here, it's a triangular shape. Y'all with me? I really confused y'all by talking to Sutton, didn't I? Yeah. I'm sorry. I'm sorry, Sutton. I confused everyone. Does everybody see that? Yes, I am recording the notes, okay? Okay. Well, I am crazy, okay? Yes, dear. Okay. How far is this distance here? It's 3. So that's how I know, okay? Okay. Look at what I said. They are isosceles right triangles. What are isosceles right triangles? Right angle, isosceles, 2 sides are the same, okay? So if it's 3 feet this way, then it's 3 feet out as well, and then we slide it back down over here. So we've got a big triangle here. Let's go back. This one is the square root of 8 long. So it's not quite as long. That triangle isn't. So then this side here is not quite as long. And it goes back down. And we've got increasingly smaller and smaller triangles all the way down. Yes, sir? Okay? When I get back here to 4, this one's 2 feet, 2 meters, 2 yards, 2 whatevers. That way. Then we're coming out 2 yards. So we've got, if I'm standing down here somewhere, if I'm looking that way, I see a massive triangle in front of me. And when I walk in, I see a straight wall over here, and I see a line down. That's the roof line I see all the way through. And the further back into the building I go, the further back in, the smaller everything gets, okay? Can you picture that now? Yes, you mean?
So that's one side of the triangle. How do you need the other side?
One side of the triangle's here, one side of the triangle's out here, and they're the isosceles, right? They're the two sides that are the same length. Then the third piece just connects it together, okay? So now, we're going to integrate dx. Y'all agree with that? 0 to 9. Y'all agree with that? How do I find the area of an isosceles right triangle?
It'd be 1/2 well, x squared of x squared.
1/2. Well, here is a formula for finding the area of a triangle is what? 1/2 base times height. Okay. Now, with a right triangle, how long are the base and the height? We don't. But it's the same height. They're isosceles, so these are the same. Base and height are the same. So we've got 1/2 s squared. Y'all with me? Okay. But now, is every triangle S? No. It's changing, right? So we've got 1/2 the square root of x squared. Okay? That's 1/2 the base times the height. Because the base is the square root of x, the height is the square root of x. Oh, yes. Why not?
So they're changing it like the same rate, so they could both
Yes.
be called x.
Yes, they're changing at the same rate, yes. Okay? And then it becomes easy. You pull out your calculator and do it. Okay? All right. Now, did the next one get ugly? Yes, isosceles right triangles perpendicular to the y-axis with one leg in the xy plane. Okay?
Wait, it's just like it's just going the points are like going the other way.
Kind of the same thing.
Okay? This yellow area is still our base down here. So, see if you can figure out what you think should be different about that and what we were just doing. Okay? Write it down. Write down what you think the answer would be. If your life depended upon answering this question, what would you write down for the answer? I'm sure you would write down something. Let's see in a second. If we're going to die, we're going to die together. Oh. Mmm. Mmm. What did y'all have? That's one thing that I see written down there.
Wait, what's the radius? Triangles don't have the radius of a triangle.
I have that one written down by someone. 9, 9. All right. Wow. Oh, I hear a lot of people talking now and jumping or saying that the 9 minus y squared is right.
Well, I'd have been shot first.
You'd have been shot first?
Yeah.
Okay. We'll pick this up next time, okay? No H45 homework due right now, okay? We'll do FRQs across the hall, all right? Yes, sir. No, they're not going to be on Moodle. They're on paper that we're doing in the class there. Where are you at this period? Okay, are y'all, well, okay. Yeah, I want you've got to limit yourself to an hour on these, okay? No more than an hour to work on them. It's kind of like a test in that respect. But you don't have a study hall at any time during the day? When do you have a study hall? 7th period? Do you want to just come to me tomorrow at 7th period and you can work on this? That'll be perfect, okay? And you're going to come to me tomorrow at 6th period, right? Okay. This, probably 1, 2 problems. And this volume that we're talking about today is probably 3 points of the entire exam. So it's not a huge part of it at all, okay? But you're going to get better at it, I promise, over the next few days. I promise you are. You'll do much better, I promise. Yes, sir.
I think so. I just played today. So I think the next week I just play it. So I think
if he's okay with you coming, you can come.
I think I can.
Okay. Check with him and see. All right. All right. I got to get over there so they can get started with their crying.
I have to make a semester test, so can I go? I think it should be
Or who?